All right, ladies and gentlemen, welcome back to another video with Mr. Kenton and HL Chemistry. And we're continuing through our discussion on periodic properties, periodic trends, and we've been taking a special look specifically at the transition metals, specifically the first row D block. And we're going to be continuing looking at our transition metals. And we're going to talk about something that's unique about them and their ability to form complex ions. Now, you might be remembering from AP chemistry when we were talking about reactions that were in equilibrium, we could get the formation of a complex ion. And so if you remember that, we're going to be diving into those a little bit more with a little bit more detail and talking about them to be able to identify some key components and some very basic ideas within a complex ion. And so hopefully by the end of this video, you should be able to explain the nature of the coordinate bond within a complex ion, and you should be able to do things like identify what's the charge, what's the ligand, what's the coordination number, things like that as it pertains to these complex ions. So I'm excited to share this with you guys because this should be pretty new to everybody. So some pretty cool stuff here. If you'd like, within this video, within the PowerPoint, there's a video that somebody put out that's embedded within it. You can go look at it and look at those complex ions key terms. You know, if you want to be able to look at that. Also, the textbook does go into some of these things as well. So feel free to use your resources to help kind of disseminate and learn that information. So let's dive in here. So a complex ion, what it is, it's essentially you've got an ion that's central to the structure. And what's going to happen is it's going to be surrounded by molecules or ions which have lone pairs of electrons around them. Okay, and the reason for the lone pairs is because the lone pairs are going to be important in being able to form the bond with that central ion, right? So kind of at its core, what you've got a central ion that's got some sort of charge. And then around that ion, you're going to have other molecules or ions that have a lone pair that surround that central ion. Think of it kind of like what happens during solvation and hydration when you've got something that's being dissolved. You've got your ion that's in the middle, and then you got the water molecules that maybe surround it and pull it away from its structure. Similar concept, but different application, right? So it just gives you something to kind of use as a reference to help you get some context to what we're talking about. Now, the reason why this is able to happen is for your transition metals, we've seen previously that they can have some pretty high charges, right? I mean, they can go up to +7 because they're losing up through their d subshell electrons. And the other thing is that your transition metals, they're getting a little bit smaller because they've got more and more protons that are in their nucleus. And so they're generally smaller in size. And so as a result, what's going to happen is that transition metal ion that's in the middle is able to interact with the ligand's lone pair of electron. And so that term ligand is referring to the molecule or ions that are surrounding the transition metal. Those are going to be those things that are interacting with it. So the transition metal is able to attract the lone pair of electrons on the ligand and form a bond with them. Okay. Now, these ligands are attached via what we're going to call a coordinate bond. All right, so let's dive into what are we saying when we talk about a coordinate bond. So a coordinate bond is a specific type of covalent bond specifically, and so what's going to happen, the lone pair of electrons on that ligand is going to form a covalent bond with the central ion and its charge. And this should give you some context. You may have heard me say before that depending on the type of element or the type of substance you're getting, sometimes transition elements can be considered having covalent bonding. Well, this is showing us how that's possible, right? And again, a ligand is a species that uses a lone pair of electrons to form a coordinate bond with a metal ion. And we'll be looking here shortly at some specific examples of some ligands that are in complex ions. So if you're still kind of fuzzy on what that looks like, we'll be able to look at some examples here shortly. And then the last thing here, the number of coordinate bonds from the ligand to the central ion is called the coordination number. And that's something that's going to be useful in determining essentially the shape of your complex ion. And the good news is some of those shapes are going to sound very familiar based on what we know about chemical bonding. So the number of coordinate bonds from the ligands to the central ion is called the coordination number. All right. Now, there are four main shapes of complex ions. So we've kind of introduced the information that we need to know about. Let's talk about some of the specifics, right? So there are four main shapes of complex ions that we can encounter. Doesn't mean that there aren't more, but these are the four ones that we're going to be focusing in on. So the first one is linear, right? So it has a coordination number of 2. So you've got 2 ligands that are surrounding your metal ion that's in the center. You get a coordination number of 2. You're going to have square planar. That's when you have a coordination number of 4. So that's when you're going to have 4 different ligands, or maybe 4 of the same ligand, that are around your complex or your metal ion in the center. That's when you get square planar. You can also have tetrahedral, which is going to have a coordination number of 4 as well. And we'll talk about the differences between the two. So, just kind of hang in there. So square planar coordination number of 4, tetrahedral coordination number of 4. Again, you're going to have 4 ligands that are surrounding that central ion. And then the last one is going to be octahedral. That's going to have a coordination number of 6. So that means that around your central ion, you're going to have 6 ligands that have formed a bond with that central ion. All right. So another thing that I want you guys to be able to do in light of the things that we just talked about is if you're given a complex ion, you should be able to deduce the total charge given, the formula of the ion, and the ligands that are present. Okay, and so let's just take a look at what does that look like. So here are some examples of some complex ions. You've got FeH2O6 3+, so that'd be your iron with water, 6 waters, 3+ ion. You got cobalt with ammonia, 6 ammonias with a 3+ charge. You've got copper, you got your CuCl4 2-. You've got your silver and ammonia complex ion where you've got 2 ammonias. And then you've got your PtCl2 NH32 complex ion as well. And so when you look at each of those, these are examples of complex ions. Notice they've each got transition metals that are attached to them. And so can you identify the ligand? So if we're looking through these, for example, like in the first one, FeH2O6, right? So the thing that's going to have the lone pairs, it's going to be the water. The oxygen here is going to have a lone pair. And so looking at that, water would be the ligand in this particular complex ion. If we look at the next one, cobalt and ammonia, right? So again, ammonia is going to have a lone pair on that nitrogen, which is going to be able to form covalent bonds with the cobalt ion. So there's 6 ammonias. So again, this would have a coordination number of 6. This has a coordination number of 6. All right, when we look at the third one, you got CuCl4 2-. All right, it's got an overall 2- charge, but the ligand is chlorine, or the chloride here, right? So the chloride's going to have lone pairs. And when you look at this, looks like you're going to have 4 ligands that are attached to it. So it's probably going to have since its coordination number is 4, probably going to be that tetrahedral. Now here for the AgNH32, your ligand is going to be the ammonia. You got 2 of them, so this one's probably going to be a linear complex ion, coordination number. And you got the PtCl2 NH32. In this particular case, it looks like we got 2 ligands, right? We've got the chlorides, and then we've got ammonia. And so you got a coordination number of 4, so it's probably either going to be tetrahedral or the square planar, right? So we were able to identify the ligands in each of those, able to look at the coordination numbers in each of those. The shape, kind of talked about that. And then the charge of the metal ion, we can look back at it. So water is neutral, It's got an overall 3+ charge, so that means that's probably Fe3+. Same thing with the ammonia. Ammonia has a neutral charge, so it's got +3. That means it's probably cobalt 3+. With your CuCl4, it's got an overall 2- charge. We know that the chlorides are each going to have -1, so we've got 2 extra. So that means that's probably copper 2+. All right, ammonia is neutral here. Silver is going to have the charge. It's just going to want 1+ charge. All right, and then for this one, you've got PtCl2NH3. Each chloride has a -1, so this is probably platinum 2+. Right? So that's how you would kind of go through and figure out what's the charge on my metal ion. You look at what it's attached to it, what's the charge of the thing that's attached to it. So like things like water and ammonia, those are neutral. But things like chloride that we have attached, we have to consider their charges as well. All right, so here are some other examples of your ligands. So again, we've got some of the ones that you saw on the previous slide. You've got like the FeH2O6. We saw it had a coordination number of 6, +3 octahedral. Same thing with our cobalt ammonia complex ion. There's your ligand, there's your coordination number, there's your charge, there's your shape. Like we said, here's your CuCl4. So here we see coordination number of 4, tetrahedral. Let's see here. You've got, an aluminum hydroxide complex ion. Here you've got an iron cyanide complex ion. There's our silver ammonia complex ion. That was linear. You got the permanganate ion. It's got an O2- ligand. So it's got a coordination number of 4. Got your nickel carbon monoxide ligand or complex ion. Now notice here for this one, doesn't have a charge, and that's okay. And then for the last one, the platinum chloride ammonia complex ion, you have 2 ligands. And so this one is what you end up with, that where it's square planar. I'll have to look into this to make sure I nail this down. Might be a correlation that because there are 2 ligands, it takes on the square planar shape rather than just being tetrahedral like all the others with the coordination number of 4. Let me look into that for you guys, and maybe I can address that in class. So that just gives you some examples of some complex ions, their coordination numbers, the charge on their central atom or ion, and then the shape. Okay, now that's going to conclude what we need to talk about in terms of complex ions. So there's a couple of skills you should have been able to pull away from that. Identifying ligands, identifying if you have a complex ion, figuring out the charge of the central ion, coordination number, and shape. Those are things that we need to be able to deduce from what you guys just watched. I hope this video was insightful. Hopefully it was helpful. Hopefully you learned some new things today. And don't forget, if you have any questions, please don't hesitate to ask. Bring them to class. I'll be more than happy to help. Thank you guys so much, and I'll see you guys again soon.